Okay, now let's look at the data structure and the null hypothesis, or the hypothesis for the t-test that we set. So we have a two-sample independent t-test. So the data structure here would be, we have two categories, category 1 and category 2. These are our categorical independent data, and we make continuous observations like that. It's very important that these observations are independent from each other, so they don't know each other, they don't influence each other in these two samples. That's why it's independent. And what we are going to do in this t-test is that we say, right, we've got two samples. We know that the two sample means, x bar 1 and x bar 2, they are most likely different because this difference is due to sampling error. But what we really want to know and what we want to understand is whether these two samples come from the same population. And in order to do so, we try to estimate the means of the underlying population. So that would be mu1 for population from which we draw sample 1, and mu2 from population 2. And our null hypothesis now asks whether the two population means, and that's important, it's the population mean, it's not the sample means, whether the two population means are the same. The alternative hypothesis in this case would be the two population means are not the same, so we can write it like that, which would lead to a two-tailed test. Or we can also formulate our alternative hypothesis as one of the sample means is larger than the other. So if we already have an inkling about that, then we could go for that, and that would mean we perform a one-tailed t-test in this case. I wanted you to actually pay a little bit attention to this two- and one-tailed tests. So that's the data structure for a two-sample independent t-test. Now in a one-sample independent test, as the name says, we have only one category, so with continuous data, so that's our category 1, which is again drawn from a population 1. And what we want to do is we want to compare our samples to a known reference value. And in a way, we treat this reference value as the mean of population 2. So in a way, it's exactly the same thing. We try from our data, where we've got x bar 1, we try from our data to figure out what the population 1, the mean of this, would be, and then compare it to the already given mean of the population 2, which is our reference value. So here we would say h0, that is again mu1 equals mu2, and this would be our reference value. So that would be for a one sample test, and again for the alternatives we would say mu1 is not the same as the reference value, or we could go for mu1 is smaller or larger than the reference value, which would lead to a one-tailed t-test. So that is the data structure for one sample independent test. Now what is a paired t-test? Well, in a paired t-test on the surface we have two data sets, again, like in the first case, two sample tests. So we've got category 1 and category 2, but the data are linked to each other. They are no longer independent. So that's the typical before and after test. And what we are actually trying to do is, instead of using this as two independent samples, we calculate the difference. So we calculate the difference C2 minus C1 for each data point. So what we are ending up with is just a sort of another category, and I'll abbreviate that with a capital. We have a category which is now different from the original categories. It's the difference between C1 and C2, between this one and this one. And our reference value, what we want to look at is, that's the reference value. We want to know whether there is a difference that is actually non-existent, whether there is a difference. So our reference value would be 0. And the null hypothesis for that would be mu 2 minus mu 1. That's the difference. That's the difference. Let me write it like that. The difference between C1 and C2 equals 0. And the alternative hypothesis is the difference of the population, or the mu of the difference population is not 0. So in a way it combines the two sample and one sample independent test, and in the one sample independent test we had a reference value which could be anything, whereas in the one sample test the reference value is 0, and our sample actually is the difference between the two categories. Now, in a chi-square test, in a goodness of fit test, again we have just simply one sort of observation. We have different categories. And we can have as many categories as we want. And we have, so C1, C2, C3, C4, and so on. And we have frequencies. These are our data here. And what we do is we compare our observations with expected values. So observed values with expected values. And that is really to test whether our observed data actually are in line with a model that we expect. So here our null hypothesis would be expected values equals the observed values, or the other way around. And any deviation from that is just due to sampling error. So that's the null hypothesis. The H1, the alternative hypothesis, is, I'll write it the other way around, observed is not equal to the expected data, and what we see is sampling error and additional factors. And of course we could, if we so want We could also formulate alternative hypotheses, but it's not very common to do that. Test of association. In this case, we have 2 or more categories, and it works perfectly well with more than 2 categories. So category 1, category 2, and again we have the same R H0 and H1.